It's a real pleasure to introduce our next speaker, Olivier Matthieu. All the information is there. Smooth dynamics versus symbolic dynamics. Olivier, the blackboard, the chalks, the audience.
Okay, thank you very much. So it's a great pleasure to be in this conference in the honor of Robert Moody. And when I was still in the kindergarten, or almost in the kindergarten, I didn't know what to do with my life. And I went to a course by Jacques Titz in '81, and it was a course about Katz-Moody groups. So that was the first time I heard about the name of Moody. And indeed, it was the first time I heard about a mathematician, maybe except cosinus professor. Okay, but today I will not speak about this topic. I will speak about something else, which is connected with differential geometry. But at the end, you will see that what's going on is a theory of arithmetic groups, means Lie theory, that we all of us love. So, but before that, there will be a long introduction about symbolic dynamics and smooth dynamics. So the talk is about the following. You start with M, be a closed manifold. And I would like to investigate connection between some differential properties of M, like smooth dynamics, connection with the symbolic dynamics of the fundamental group. And indeed, you will see there will be two sets of conjecture and theorem. So the first is a connection between Anosov theory. So this is a dynamical property of manifold, which will imply some symbolic property for the fundamental group of M. And here I will have a conjecture, and a part of this conjecture is proof, so it will be a theorem. So it's a set of conjecture and theorem. And there is a second thing, is that some symbolic property for pi1 of M for some special spherical manifold will imply the existence of affine structures and affine structure. And and this is a way, this is connected with what was called Milnor conjecture. But most of my talk will be about this part, because this one is a little bit more simple and maybe so. So first, I would like to explain what the symbolic dynamics for group is. So I start with of groups, which means self-similarity. At least in my talk, and by this I mean self-similarity. So I take So I start with a group gamma. Usually it's by this I mean a discrete group without topology. I start with a finite alphabet. A finite alphabet is the same as a finite set. And let's define A omega be the set of infinite words over A. And by infinite words, I mean semi-infinite words. So for example, if A equal just the set with two elements A and B, an element of the type A, B, 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 let's say B, A, B, 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 and so on. This is an element of A omega. So it starts at some point. There is a starting point, but there is no end. Okay, this is a semi-infinite word. And you assume that gamma, so an action of gamma, of the group gamma on this A omega is called self-similar if and only if for all G in gamma and for all A in A, in the alphabet, there exists GA, no, sorry, there is B in A, and there exists GA in gamma such that J acting on A star omega star W equal B star GA acting on W for any W in A omega. So what's the meaning of this? This is a concatenation product. So you take an infinite word and you put A in front of it. And the dot here means the action. Okay, so this is a definition of a self-similar action. And
depends on A.
Which, this one?
B,
Yeah.
and B depends on A.
Yeah. B depends on A and J, and GA depends on A. And let me say that A, now I need to define what a minimal action is. So let me remember that A is a topological, A omega is a topological space. For example, the simplest way to define the topology on A omega is to define a metric. And simply if W and W prime are in A omega, you say that the distance between omega and omega prime is 2 to the minus n if the first n letters are equal, are the same. But not the next one. Okay, so the distance of A, B, blah, 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 with A, blah, 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 this is 1/2. because you see, the first letter is the same, but the second is not. And this is, of course, an ultrametric. Sorry?
What is the G on the left-hand side of that?
This GA
No, the one to the left.
here?
Yeah.
Yeah.
Oh, okay.
For any J in gamma, any A, there is, symbolically, you can write it. This identity is sometimes write it like GA equal B GA. Sometimes it is, this property is written like this. Okay. And so a minimal action means that the orbits are dense. For example, you can say all orbits are dense, but because it's an ultrametric, because it's not a metric, ordinary metric, but an ultrametric, if one orbit is dense, all orbits are dense. So it's really not a problem. Okay. So now we know the main notion of symbolic dynamics for groups. I would like now to define some smooth dynamic, which is indeed some C1 dynamic. It's not exactly smooth, it's C1 dynamic for M. Sorry? Yeah, the root. What? But there is no, but this is geodesics. A omega is a set of geodesics, there is no root. So, sorry? But no, but it's not a tree. It's a border of the tree.
Yes, but the actual self-similarity, I think, is well.
Of course, you can see it, but as you will see, if I define it on the border of the tree, there is some, okay. You will see why I define it on the border of the tree. And I will tell you exactly why. Now you have the C1 dynamic for theta. Now you assume that M is a closed manifold, closed, smooth manifold. For French speakers, closed means compact, without boundary. Okay, and you take theta, a diffeomorphism of M, and by definition, you say that theta is anosoph if there is a decomposition of the tangent bundle Tm as a sum of two subbundles EU plus ES, such that satisfies the following property, that d theta restricted to ES and d theta minus 1 restricted to EU are contracting for some Riemann metric on M. And so that's the definition of anosoph diffeomorphism. From time, quite often, you start with a metric And so you can guess what could be the corresponding condition. But it's strictly equivalent to the original definition because M is closed here. What is very important here, theta should be at least C1 or smooth. It does not change too much. It's not a big deal. At least if you look at the theory, it does not change. There is no big difference between C1 and smooth up to now. But what is very important is that the decomposition is only a continuous decomposition. And this is important. It's important not to assume more than that, because it turns out that when you look at generic anosoft diffeomorphism, then the decomposition is only C0, even if you start with something smooth. There is no way to get rid of this condition. And it's really important. This condition, to assume only this is very important. So and now my first conjecture is the following. Conjecture 1. If M is, so let M be a closed manifold, then if M is anosoft, by this I mean if M admits some anosoft diffeomorphism, then P1 of M acts on self. There is an action. There is a free minimal self-similar action of the fundamental group on A omega for some alphabet, for some finite A. Now I will answer Bertrand's question. Bertrand said all self-similar action came from an action on the tree and so something like this. But I will ask Bertrand, if you want to explain what a free action means, stabilizers are 0 at the level of the tree, this is a horrible condition. Okay, so I don't want to speak about trees because of that. Minimal is relatively easy, but it means that it is transitive at each level. But free is horrible condition. So that's why I was not happy about your question in some sense. Okay, so that's my conjecture 1. And now I will explain a theorem which is very close to a solution of this conjecture. And this is a theorem 1. So for the theorem 1, I have M anosoft manifold so closed manifold And I do consider M tilde, this is its universal cover. Of M. And the theorem is that. So the theorem is that the conjecture holds whenever two conditions are satisfied. So assume one, phi1 of M is torsion-free and virtually nilpotent. By this, virtually nilpotent means a finite index subgroup is nilpotent. Second condition, the cohomology of the universal cover, say with value in Q, is finite dimension. Assume that the universal cover is a finite Betti number. Of course, for, sorry, M tilde. Of course, M is closed manifold. So M, cohomology of M is as finite Betti numbers, but for M tilde, it's not always the case. And then conjecture one holds. Now we can ask, are these conditions strong conditions or really very reasonable conditions? And I would like to show you that this is a very reasonable set of conditions, because there is a classical conjecture by. So let me explain first the notion of infra Nil manifold. So you start with N, which is a connected and simply connected Lie group. And let, I don't know, usually people give it another name, but I never understood. The affine group of M means it's a group of automorphism of N semi-direct product with translation. So this acts over N, this acts by translation. So don't ask me if it acts on the left or on the right, because new mathematicians don't know the difference, but it acts in a certain way, and the automorphism acts naturally. And you can make this. And now, Infra Nil manifold is a manifold M, which is isomorphic to N divided by gamma, where gamma lives inside the affine group and say it should be say the action should be with proper and co-compact action. But by this, no, sorry, not exactly, like in a way that gamma intersected with N, now the condition is the following. Gamma intersected with N, which is gamma 0 by definition, should be is a co-compact lattice in N, and gamma 0 has finite index, and gamma acts freely. Conditions that gamma acts freely is necessary to impose that this is a smooth manifold. Okay, so this is a definition of infra Nil manifold. So the pi 1. So you see that you know that because N is simply connected, pi 1 of M, of course, is gamma. And this gamma is torsion free and virtually nilpotent. Let me give one example because it's very unclear. You see, essentially, this group is a semi-direct group. And you see that gamma modulo gamma 0 would be, in some sense, a finite subgroup here. So how you can have a finite subgroup and torsion free? But indeed, it's not really a finite subgroup. So one example is N equal R2 and gamma 0 equal Z2, and then you add the following element S, which is the following. It's an XY to X plus 1/2 minus Y. Okay.
Is capital N nilpotent?
Oh, sorry, nilpotent. Yes. Sorry. So, and S is this thing. So now gamma can be gamma 0 union S times gamma 0. This is clearly a group. Okay, the group generated by translation and this thing. And then you see that really the action that you see that this group has no element of finite order because when you take S square, this should be the translation by 1, 0, something like this. And so it has infinite order. So it does exist. But it's very logical because you see when you extend that here, this is a split semi-product, but when you take a lattice, it could be not of the same type. Okay, so now we know what infra Nil manifold is, and now there is a big conjecture and a classical and big conjecture. Due to small Anosov small conjecture, which dates back from the 60s, I believe, very old conjecture, but which is the main conjecture in the topic, is that Fm is Anosov if theta and Anosov homomorphism on M, then topologically M is an infra Nil manifold And theta is what is called an Anosov automorphism. But here we don't need to know the end of the conjecture. But what is very important is that if, so the conclusion of this is that if M is, so it implies that if M is Anosov, then M is homeomorphic to an Nil manifold, infra Nil manifold. What is very important is that here the conclusion is that M is homeomorphic to an infra Nil manifold because there are non-example of exotic tori, means closed manifold which are homomorphic to tori but are not diffeomorphic to tori, which have Anosov diffeomorphism. These examples are due to Jones and oops, I'm sorry. Sorry? Farrell and Jones, exactly. Farrell and Jones. Yeah, thank you very much. And so you see that immediately now the conclusion is that Anosov small conjecture plus theorem 1 implies conjecture 1. Why it is so? It's because for an infra Nil manifold M, pi 1 of M is torsion free, and the universal cover is contractible space, even there is no cohomology, except in degree 0, of course. So this condition is less than what is required. Okay, so this is really, so it shows that this conjecture is, in some sense, very reasonable conjecture. And that the theorem is, So now I would like to say a few words about the proof of the conjecture. And at the end of the proof, you will see the appearance of some result about arithmetic groups. So I would like to say something about the proof. So first, you have theta, Anosov diffeomorphism on M, and gamma is a torsion-free nilpotent group. And especially gamma contains gamma 0. There is always a subgroup which is nil radical. It means, no, sorry, the unipotent radical. Sorry, gamma, yeah. It means the biggest unipotent, nilpotent, no, sorry, yeah, no, nilpotent. So it's the biggest nilpotent invariant subgroup. It's very easy to show that it does exist and it's always exists. So now I want to say that theta gives rise to an theta equal theta star, which is an automorphism of gamma, of the functional group. Okay. Strictly speaking, say assume that theta is a fixed point. Okay, then in that case it's very easy. So if theta is a fixed point for some x in M, then of course theta acts on the functional group based at point x. It means all loops starting at x and ending at x. And of course, there is an action of theta on this, so there is an action of theta on the homotopy class of this. But in general, this is well defined up to inner automorphism. It's because you are okay. This is not a well. So theta star is not a well-defined thing. It's defined up to some inner automorphism. But what we have to see is that theta what is important that theta star is an automorphism of gamma 0 modulo inner automorphism. Now, since gamma 0 is a nilpotent and torsion-free group, there is a unique nilpotent connected and simply connected group, Lie group, such that gamma 0 is a co-compact lattice in N. Some people call this a Malchev theorem. But I believe it has been also noticed by other people. But this is a classical result which dates back from the 70s. Now you have an automorphism of the Lie group. So now theta star will give you an automorphism of the Lie algebra N of N. Again, it is automorphism modulo inner automorphism. But the spectrum, of course, by this I mean the spectrum of theta star over C. Okay, the spectrum of theta star is well defined. Because you see that, okay, it's basically, yeah, if you multiply theta star by an inner automorphism, it does not change its spectrum. And the first step of the proof of first step is the following lemma, which is that spectrum of theta star contains no root of 1. I have to say that for Nil manifold, for tori Nil manifold, it's a theorem. It is due to Frank and Manning. Again, this should it should be in the 60, very old result of Frank and Manning. Frank proved it for tori and Manning for Nil manifold. But I have to extend this in general, and okay, I will not say too much. Yes, of course.
So when you say the spectrum of theta star, the spectrum of the operator associated to theta star or L2N?
No, the spectrum. No. Okay, theta star X is a linear operator on N. Say, take the complexify. It's a finite dimensional linear endomorphism. So you just take the set of eigenvalues with multiplicity or things like this. So that's
If you take a power of
sorry?
if you take a power of another diffeomorphism, it's still another diffeomorphism, right?
Right.
So I mean, if you have a lot of unity, you can derivative by taking some power.
Right.
So why is this lemma so useful?
Why is this lemma?
So useful since you can always take some power from
Right. Yeah, it's the same as saying that one is not in the spectrum of theta.
Okay.
It's really the same.
Okay.
And this is a basic idea of Manning and Franks. But here I will not explain the theorem, but say basically the trick is by using some Borel-Serre fibration. Yeah, basically when you take M, okay, no, sorry. Assume for simplicity, we can assume for simplicity that P1 of M is this group gamma 0. Up to some covering, it's correct. It's okay. Then now you know that you have a, this is a the first step of Postnikov tower. You have a map from M to N divided by gamma 0, and the fiber is M tilde. And this is a homotopy fibration. And this map, this fibration is unique in the homotopy category. So it's a well-known fact. And because this is K, the KP1, K gamma 0, 1. You have always a map from a manifold to the KP1, and the fiber, homotopy fiber, is the universal cover. Of course, it's a homotopy fiber. You don't expect to have a real fibration. If you look at the dimension, most of the time it's strictly impossible. Okay, so just homotopy fibration. But anyhow, so you have associated to this, it means that the cohomology of M with value in Q, you have a spectral sequence, and the term E2PQ is something like the cohomology of gamma 0 with value in, so HP in value in HQ of M tilde. And I put a double bar under that, or the cohomology of, say, cohomology of N gamma 0, this. And by this, I mean, what is this? This is local system. It's not, because here it's not simply connected, so it's not exactly constant cohomology with constant structure, but it is a cohomology with value in a local constant structure. Okay, anyhow, by using this, I can prove that the Lefschetz number for theta star divides the Lefschetz number for theta. After some, it requires some proof, but I can use this to prove that the Lefschetz number divides this one, and therefore, since this Lefschetz number has to be non-zero, this one has to be non-zero, and this, and then this is enough to prove that one is not a root in the spectrum. This is a trick of Mannings and Frank. So that basically is the idea. Now I would like to explain what a self-similar structure is. So now you have a group gamma, and you want to, and there is a notion of virtual endomorphism, which means a map F from gamma prime to gamma, where gamma prime has finite index in gamma. And if you have how it is called, a self-similar action, of gamma on A omega, then you can define gamma A, the set of all, and A is in A, the set of all gamma such that gamma of A equal A. You should notice that since gamma acts on A omega, indeed it acts on the set of alphabet. And this is a subgroup. And now the map G in gamma A to GA in gamma is a group morphism. You see, the map G on GA is defined on gamma itself, the whole gamma, but it is not a morphism of group. But when you restrict it to the stabilizer of one element, it is a group morphism. And it has been proved by Sitki, Nekrasevich, that essentially a self-similar action which is transitive on the first level, it is the same as a virtual group morphism from gamma A to gamma. Okay. But of course, in general, this, if you have a group morphism from some subgroup to gamma, it will give you a self-similar action, but most of the time, this self-similar action is neither free, neither minimal. It's just transitive on the first level, that's all. And now, we have my theta. And exactly here, the alphabet, of course, is gamma modulo gamma. Here I have my theta tilde, which is essentially an automorphism of gamma. And of course, as a virtual endomorphism, it has no interest because it does not give you any self-similar action. It gives you a trivial self-similar action. And what you want to do is, starting with this theta, you want to build something more interesting. And that's where the theory of arithmetic groups is involved. And now, so from this given theta star, I want something more interesting, more something else, another. I want a virtual, a good virtual endomorphism. And now I would like to state the theorem about arithmetic groups I have in mind. The theorem is the following. So for the theorem, I need some new hypothesis. So H now will be a torus, algebraic torus, defined over Q. X will be the group of characters, algebraic characters, of course. But you have to be careful that when H is an element, is a rational element in H of Q, and chi is a character, chi of H usually is an element in the algebraic closure of Q, but it's not always in Q itself, because the torus, most of tori are not split. Okay, so it's an algebraic number, but usually it's not Q. And the theorem is the following. Theorem, there is, so let n be greater than 1 an integer. Then there is there is some element H in H of Q satisfying the following two conditions. I. For any chi in X, chi different from 1, chi of H is not an algebraic integer. So it is not an algebraic integer. It is an algebraic number, but not an algebraic integer. And second condition is that in some sense, chi of H for all chi of H is congruent to 1 modulo n. So I will explain what this condition means. So let me explain a bit more what this condition means. It means that, so when I take, so there is a K is an extension of Q such that H over Q split. So a finite extension which satisfies this. And O is a ring of integer. So it is always the case that chi of H belongs to K. So the first condition is that chi, so I means chi of H belongs to K, but not in O, so ring of integer. O is a ring of integer of K. And the second condition means the following. It means that for any pi dividing n, for any place, finite place dividing n, so I never knows if it's a place over anyhow. For any place dividing n, chi of H should belongs to the ring of pi integer, and chi of H is congruent to 1 modulo n of pi. So there is a finite number, of place dividing n, and for each of them you should satisfy this condition. And now what's going on is that I start with, yeah, you have still 2 minutes, so it's perfect. I start with theta star. And from theta star, I take its semi-simple part. So G, the semi-simple part. So let me remember that theta star belongs to the algebraic group of automorphism of n. So there is a Chevalier decomposition, theta star equal, how to call it, theta 1, theta 2, where theta 1 is semi-simple, theta 2 is unipotent, and they commute. Maybe we can say this is Jordan decomposition, but usually it's called Chevalier decomposition. But it is Jordan decomposition of endomorphism. This is well known. And now I take the group. I take the semi-simple part. I take the algebraic group. I take all power of theta 1, and I take the Zariski closure in out of n. And this is H, no, maybe K. But this K is not necessarily connected group, but there is a finite subgroup, a finite index, which is the connected component of K. Oh, sorry, K is not the same K as before. And so let me call H prime. So this is a connected component, and this is by definition, H is a torus defined over Q. Okay. And now inside this torus, I can define a new element which satisfies this condition. I will explain what N is, but this condition, this will ensure that the action is free. The corresponding, the phenol self-similar action is free. And this condition is for the minimality. So basically, for free action, we have one, oh no, sorry. This is, I don't want to say anything more. I cannot explain where this number n comes from, but in this construction, there is an n occurring at some point. And when you have automorphism satisfying this condition, it will mean the corresponding self-similar action will be minimal, and this is for the freeness. I could not give more details, but just let me say that this is the main idea of the proof. So basically, up to some starting point, which involves some easy algebraic topology, at the end, the heart of the proof is based on some property of arithmetic groups. But the proof is very long, so it's difficult to explain why these two conditions are really important, but you see at least what is the use of these two conditions. So thank you very much for your patience.